Hey guys, what's going on? My name is Kyle, and today I'm going to talk about clean architecture, theory, and concepts. To summarize this, I'll first introduce software architecture, briefly talk about software architecture, and then I'll get into the clean architecture section. Software architecture. So according to Gerald Weinberg, if builders built buildings the way programmers wrote programs, then the first woodpecker that came along would destroy civilization. So this is a very interesting statement here, because when we think about a building that is being built, or uh, a house that is being built, we would assume that project was very well defined, very well structured, very well planned. You might have architects, civil engineers, um, you have construction workers with all their experience, and multiple people involved on a project like that, right? So that when that building is constructed, it won't, it will be a safe building. Um, People won't be scared of getting into it, and if something happens to that building, people might, die. So when we think about programmers or programs, sometimes not too much planning goes into writing programs, right? Depending on the person who is writing them, of course, and sometimes also the organization that is planning to write that program. So, sometimes speed over quality is, what programmers would rather have in their applications. They would rather deliver fast than plan, analyze, and deliver the best result, right? So this is a very interesting statement here. So when we think about the architecture project, it describes how a system is organized and the general structure of a system, right? So the architecture project is a creative process, right, where somebody, designs a system to satisfy requirements, functional requirements or non-functional requirements, right? And we can see here that we have a MVC application. So we have a view, a model, a controller. The browser will show that view. um, it requests actions to the controllers. The controllers can make use of models, and those models can be displayed on the views. And let's assume that, I'm creating this architecture here. I'm defining the responsibilities of these layers. And during a meeting with the developer, he comes to me and say, hey, the model is not actually a database representation. It represents the view in my point of view. It represents what data is being showed or is being displayed on the browser, right? And sometimes that data is not an actual database representation, right? It's not true to that. So, we can make changes to the responsibility of that layer, right? So I can say that a model now, based on that meeting I had with a developer, defines a data structure, right? So we can discuss layers, we can discuss responsibilities during, the architecture project, and better define the responsibilities of layers to deliver the best result, and that the whole organization or the whole team working on the project can fully comprehend, and implement the responsibilities for each of these layers. So this is a very simple um, architecture, right? MVC, which is model view controller, very simple. However, when getting into discussions, getting into requirements, getting to understand these layers, it can it can not it's not going to be complex, but changes can occur, right? It can evolve, right? And things like that. So when we think about architecture rules, according to Uncle Bob, the rules of software architecture are similar between different types of systems. So this is very interesting, based on Uncle Bob's experience, more than 40 years of experience, where he worked on games, he worked on mobile applications, console applications, and he realized that, the rules that he is implementing for one of these systems doesn't change that much, or they have many similar, concepts between these different types of systems, right? So if you have good fundamentals of software architecture, these fundamentals can be reused between different types of systems, right? It's not that you have to architect based everything based on, the type of system that you have. Some systems, like some types of systems, might, you know, make use, or it might be better to use certain concepts of architecture, design principles. However, based on Uncle Bob's research and experience, um, most, there are a lot of similar implementations that can be used between these systems. So the goal here is that of software architecture is to minimize the human resource required to build and maintain the required system, right? So the less resource you have, the more money an organization will save, the more projects a developer can work on, the less bugs you'll need to you'll need to fix, right? It'll be easier to fix bugs and things of that nature. So now we're going to get into the clean architecture part, and I'm going to talk about some of the theories and concepts that are presented on the clean architecture book from Uncle Bob. So one of the chapters describes the solid design principles, which I think is very important for every software developer and architect to fully comprehend, revise, and always, have all of these principles um, in the back of your mind, right? Not in the back, but always think about these principles when implementing, designing software. Today I'm going to talk about two of these principles, which is the single responsibility principle and the dependency inversion principle. However, I would highly recommend for, if you don't know these principles, to revise them um, and look over them and understand them. So when we think about the single responsibility principle, it states that a class should have one and only one reason to change. Many times this is um, interpreted uh, as a class should have only one responsibility, or a method should have one responsibility, and that is wrong, right? It states that a class should have one and only one reason to change. When we look at this image here, we can see that we have three users or actors. We have a parent, a student, and a school, right? And these users makes use of a student class. And this student class, for example, the parent makes use of the get absence because he might want to know, if his kid is going to school. The student wants to know wants to calculate the grade point average because maybe he wants to go to college, to a university. The school wants to get the ranking of that student um, because the school might want to print that on the report card, right? So we have three public methods here and a private method, which is calculate grade average. So two of these public methods, which is the calculate grade point average and the get ranking, makes use of the calculate grade average private method. Now let's assume that the business rules change for the get ranking, right? And the developer who made this change, he updated the private method called calculate grade average. So he was able to fix, right, or he was able to fulfill the requirement for the get ranking. However, he broke the calculate grade point average method. The unit test didn't catch that, right, and wasn't he wasn't careful enough to make tests to make sure that the calculate grade point average didn't break. So to resolve this problem, we can create applying the single responsibility principle, right? We can create three different classes, right? We can create a student grade calculator class, a student ranking class, and a student status class, which has those public methods. And then if we need to reuse an object like the student model between these classes, we can create a separate class for that and make that, that reuse. Also, if you have, if these classes are being instantiated constantly, you can implement a facade, right? And that will reduce, the number of instantiations that you have. Of course, the facade won't have much implementation in it. It just maps to the classes, right? the student grade calculator, the student ranking, and the student status. So based on one principle, which is the single responsibility principle, that states that a class should have one and only one reason to change, we created three separate classes for each actor, right? That one reason to change. We implemented a facade design pattern and we created a bottle class. So based on one principle, much improvement was done. And this is something that might not be very common for a lot of developers, right? So maybe you're a developer, you're working on a project, you're fixing a bug, right? And you're working on private method, and you want to fix that bug really quick, right? Maybe maybe it's in production, or you just want to fix it really quick, and you make a change to a method that is being used throughout multiple classes, right? You make change to a private method which is being used throughout multiple classes, and you just make that change, right? You don't care who's using that class, and you make that change, you release that code, it goes to production, everything works well, the user is happy, but you might have introduced new bugs to other classes, right? So when we think about this principle, when we apply this principle, we improve our software, we improve the maintenance of the software, we improve our overall architecture, right? So it is very important to understand and apply these principles because they come in handy, right? So when we look at the dependency inversion principle, it states that flexible systems should have source code dependencies on abstractions and not on concretions. So we have a simple example here where module A points to module B, which they are concrete methods, right? However, we would want to apply this principle. So to fix this, we can have module A make use of an interface and module B implement that interface. So now we can unit test easier, right? We can change the implementation of module B. We can change technologies. So we have a lot of flexibility here. And so this is a very important principle when we think about, architecture. And then Uncle Bob goes into the component principles on, couple of chapters, later. So components are the units of deployment. They are the smallest entities that can be deployed as part of a system, right? Well-designed components always retain the ability to be independently deployable and therefore independently developed. Here we have three examples of components, one in .NET, which is a DLL or a NuGet package. There's one in Java for jar files, and there's also an example in Ruby that are gem files, right? And then he states that components should be cohesive, right? So which classes belong to which components? When we think about the at a software development level, sometimes, at least I have, or I had, and I have, problems naming classes and naming things, and sometimes software architects, they have, they might run into, difficulties in trying to figure out which components they should create and which classes should go in these components. So, I mean, it's a nice problem to have, right? And Uncle Bob's, he helps us with some simple steps, right? So he states that there exists, he states three component cohesion principles: the REP, which is a reuse and release equivalent principle; the CCP, which is the common closure principle; and the CRP, which is the common reuse principle. So the reuse release equivalent principle states that people who want to reuse software components cannot and will not do so unless those components are tracked through a release process and are given release numbers. Software developers need to know when the new release are coming and which changes those new releases will bring, right? So let's look at an example here. So we have an API and a console application that makes use to an account service, right? So it uses the component, the business component that has a account service class in it. Now let's say that we updated the account service, and that update actually broke my API, right? It broke an endpoint of that API. However, it did not break the console application. So to apply the component release principle and fix this issue, we could version that component, that business component, right? So we could have the business on version 1, which is the original version, and then business on version 1.1, which is the one that broke the API. And then if we need to update, the API to the newest version, we can retest all of those endpoints that are breaking. The common closure principle states that a component should not have multiple reasons to change. So you would want to gather into components those classes that change for the same reasons and at the same time. You will want to separate into different components those classes that change at different times and for different reasons, right? So here we have another example, which we have a web presentation layer, which has a contact module, right? And that contact module makes use of the business layer, which has a contact service and has a public method that fills a contract drop-down list. So that module would pass to the contact service a drop-down list as a parameter, and they will fill that drop-down list with contact information, for example, right? So this is an issue. Why? The issue here is that if we have other presentation layers, like a mobile presentation, that does not use does not use a component, called drop-down list, that contact service fill contact drop-down list will not be used by the presentation mobile component, right? So this is an issue, right? And to fix this, applying the common closure principle, we can create, a contact service that returns a list of contact, and then that list can be reused on the web and the mobile presentation layers. And then we can do whatever we need with that data, right? We can fill the drop-down list, fill whatever list is being used on the mobile application. This seems to be something that people won't do, right? Developers won't do, but I have seen some code very similar to this, right? Very similar to this problem. I have seen code implemented very similar to this. And so these principles are very important for developers to understand, so they can create classes that make sense on each components. So that's why it's important to architect layers and components that has responsibilities applied to them. And the last principle here is the common reuse principle. And it states that classes that are not tightly bound to each other should not be in the same component, right? So we have an example here. So we have a component A that has an email service, and then component B, which has the email implementations, right? And it also has IO and formatting implementations. So let's assume that the IO and the formatting or formatter implementations are updated constantly. So each of these updates, let's suppose that they will cause, the component B to update the version. And when that version updates, we would have to retest component A, right? So we have a problem here that the common reuse principle, if applied correctly, could solve. So to solve this, we would create a third component, which would have the email implementations, and then component A would make use of that component, and then as component B would update, we won't have to retest component A. So applying the common reuse principle, we would fix this, right? And this is also reason to create new layers and components, right? We're not creating it out of nowhere. We're applying a principle to create new layers. So now we close the clean architecture part from Uncle Bob. Now let's look at clean architecture based on this book from Steve Smith. He states that clean architecture is a domain-centric approach to organize dependencies. So you can download this book. This is actually a free ebook. It's based on web applications with ASP.NET Core and Microsoft Azure. And there is a clean architecture chapter on there. So he states a lot of common design principles. If you're listening to this and you're a developer, I highly recommend you to review these principles. And they are stated here. Some of them are encapsulation, explicit dependencies, the dry pattern, don't repeat yourself, and bounded context. So now let's get into the typical application layers, which Steve shows us in the book, right? So he states that the UI, that typical or legacy, some legacy applications, they use this pattern here, right? So we have an UI, we have a business logic layer, and then we have a data access layer. In the business logic layer, they access the data access layer through concrete methods and not through abstractions. So the tests that we would want to create for the business logic, they would depend on data access, right? So it would be really hard to create tests when we have a structure or a architecture like this one. And then you would also have compile time dependency on the data access layer. So clean architecture puts the business logic and the application model at the center of the application. Instead of having business logic depend on data access or other infrastructure concerns, this dependency is inverted. Infrastructure and implementation details depend on the application core. So what he means by this is that, we can have the user interface and the infrastructure point to the business, right? So now the infrastructure, when I say business, is the domain, the core of the application. So now the infrastructure, can implement, email services, queries, database, right, queries, and the infrastructure also has the power to change these technologies, right? So you're not database dependent, you're not framework dependent here. You have a more flexible system, right? When we look at these rules, we would want business logic and entities in the core, in the center of the application, right? The core cannot have dependencies, and then other layers would depend on the core. Inner layers would contain interfaces, outer layers would implement. And then here we have an onion view of the clean architecture, right? So we would have the core in the center, and then we would have the user interface and infrastructure on the outer layers, and they would point internally to those layers. They would point to the internal layers, right? Here is another view, a horizontal view, where the user interface has an optional compile time dependency for infrastructure, if it is being used or not. And then you have, the user interface also have that dependency on the application core. And now you can easily create mocks on the application core, easily create mocks and test the application core. We also have an example here using, ASP.NET. So for the presentation layer, we have, a web app with, your controllers, your views, your identity. For the infrastructure, you have, your database configurations like Entity Framework Core. You have your service bus configuration like Azure Service Bus. You have your, your SMS, email services, and other, API clients. And then on the core, you would have your business services, your interfaces. If you're using DDD, you could have your, domain events, aggregates, and all your logic. You don't have to use DDD for a clean architecture, but here there is some DDD concepts. The advantages of implementing clean architecture is that it would be loosely coupled. You would have the power to update infrastructure, so you would be framework independent and database independent, and it is also highly testable, right? Now let's talk about the principles that was presented in the beginning, right, from Uncle Bob's book, that were applied on Steve Smith's book. So we can understand how theory, right, goes into practice, how theory goes into implementing these things, using these architectures. So when we look at the infrastructure layer, we have the UE with that optional compile time dependency. So on the UE layer, we can implement dependency injection and define, which database we want. I can have, I can use an Oracle database, I can use a MongoDB, I can use an SQL server. And this is part of the dependency inversion principle, because on the infrastructure layer, I would have those implementations, those concrete implementations, but I also make use of abstractions for those concrete implementations. For the common closure principle, I can have my infrastructure, right? And then I can have an infrastructure data layer that would be responsible for data access, for example. And then on this layer, I could have, classes that are tightly coupled to to data access. So I could have my repositories, my context, or my unit of work, right? I don't want to have, for example, email things on this layer, right? I could also implement, it was also implemented, right, the reuse and release equivalent principle on the clean architecture, right? So you can have infra data, and then you could have infra service bus, which with your service bus implementations, and infra communication with like email services, SMS services, and then you can version them, upgrade them, and evolve them as necessary. Finally, the common reuse principle, where we could implement these layers, right, and then use them. We could have our UI, for example, my API use the infrastructure data. I could have my web use the service bus and the data, and my console only use communication for email, right? Let's say he just want to send emails. So, I mean, we could have the reuse principle easily implemented, right, and make our structure more organized, right? We could evolve this without having breaking changes between UIs. So, as you could see here, when we looked at the fundamentals of clean architecture, the fundamentals of theory, we could apply those theories to clean architecture. When applying those theories to an architecture, to a project architecture, we we would get the result of clean architecture. So clean architecture is based on, the architecture design principles, right? And then you could evolve your clean architecture based on your organization needs, based on your project needs, right? So we could have kind of what I would say variations of clean architecture. For example, here we have a clean architecture to the left that has, enterprise business rules, application business rules, interface and adapters, frameworks and drivers. And by applying, architecture principles, this organization here could evolve this architecture based on their needs, right? Also, we have one to the right, which has an application and domain infrastructure presentation. The concept is the same. However, you could implement each of these components. Inside each of these components, you could have, different layers that would, apply to these components, right? So I could have layers in my domain, I could have layers in my application, layers on my infrastructure that applies design principles that make sense and they are easy to, they would be easy to do maintenance and understand and evolve based on the design principles that we talked about here. So what I'm trying to say here is that, it is important to implement clean architecture. It is important to understand this clean architecture, but it is also important to understand the principles, because that will help you evolve your application. That will help you grow your application. That will help you understand why you have the layers that you have in your project. To conclude, um, Uncle Bob states that when software is done right, it requires a fraction of the human resource to create and maintain. Thank you very much for watching. Don't forget to like and subscribe.